Hi everyone, so we're going to have a look at using ENGRID to make a mesh for OpenFOAM, and I'm using this in Windows because the current best build of ENGRID, the latest version 1.5, is only working well in Windows, and ENGRID is in need of a bit of development work, and at the moment, because of the ways various dependencies are built up, it's very difficult to install in Linux right now. It's not impossible, but it's a little bit of an advanced user project. So I'm just going to run it in Windows, and I suggest you do the same. So you can get the download link for where to download the Windows from my website if you look in the text under the video, and just install that. So there's a couple of little handy hints. So you can see there's the ENGRID icon on the desktop. One important thing is you must every time run it by right clicking run as administrator. If you don't do that, you will get really annoying bugs with failure to save, so make sure you do that. So the basic workflow with ENGRID is a little bit different if you use the snappy hex mesh. So basically the workflow is we get the STL file, we make a surface mesh, and then basically what we're going to do is we're going to create one very thick prismatic boundary layer which will later subdivide. Then we're going to make the volume mesh in the middle, and then we're going to subdivide the boundary prismatic layer into however many layers we want. So this is why you get a good behavior with the boundary mesh, because we don't move the volume mesh inside like we do in snappy hex mesh when we add more layers, which eventually just causes you to get horrible problems with orthogonality and skew depending on what the geometry is like. Unless it's very smooth and absolutely perfect, it's really bad. Unfortunately, one of the downsides of the ENGRID is it's pretty slow. So I've saved this at various stages, so I'm not going to sit and make you watch ENGRID calculating the mesh. I'll just tell you how to do each step, and we can see the results, and then I'll load the next step in just as a quick video. So the first thing we're going to do is we need an STL file, and you need to make sure that has been converted to meters, otherwise that's going to cause problems. So let's just import STL, and that's my STL file which I've already converted to meters. So just click OK, and this is our main window. It's very much just like a CAD screen, so it's just left hand mouse click, hold the button down and move it around, and you can spin the model around. Middle mouse button, drag it around, mouse wheel scroll, zoom. It's pretty standard. So the first thing to do is really just to have a check that we've actually scaled everything correctly. So go view, coordinate axis, and it should be very obvious to you based on whatever it is you're meshing if this is correctly scaled. So that wants to be in meters. So there we go. So the first thing we're going to do is basically, unlike snappy hex mesh, this is a binary STL file, so we can't import ASCII STL files with all the patches named by hand like we would do with snappy hex mesh with multiple patches. So this is a single binary STL. So that's a bit tricky because obviously we want different patches for the inlet and the outlet and the main wall. So it does come with a feature angle recognition to enable us to do that. So basically that's the first thing we're going to do. So move the mouse over each patch you want. I would recommend attempting to make sure that you've got a clearly defined edge around each different patch. That may not always be possible, but there are different feature angles to play with if you want to change that. So I'm going to move it over what I think is going to be the inlet, and basically just press P. So then a little red blob appears on that surface, just letting you know that ENGRID knows it's going to do something with that surface. and then we're going to do just type S on the keyboard, and we've got a feature angle which is just going to look at what that angle is at the edge of this patch, and it's then going to recognize, oh, that's the edge of the patch. So boundary code, this just wants to be a list of ascending numbers, so the sensible thing is just to start at 1 and go upwards. I'd leave all the other things by default for this particular case. I'm just going to say OK, and that's then hidden that, which just is a nice way of saying OK, I've assigned that as a patch, so it hides it, which is a nice way of making sure that you go through the model from start to end and don't miss anything. So let's do the main wall now. So again, I'm going to hover the mouse over it somewhere, press P on the keyboard, then press S on the keyboard. We started at 1, so I'm going to make this 2. All other options default. OK. Last one, the outlet. Hover the mouse over, press P on the keyboard, selected it, press S on the keyboard, set the boundary code to 3. If I had more than this would next time be 4, 5, etc, etc, etc. OK. So we've done that now, and you may now think, well, where's the mesh gone? It's all vanished. So if you just either go view boundary codes or press the keyboard shortcut V, that's saying they're hidden, so we're going to unhide them all, and they're all back. So now what we're going to do is tell ENGRID which size of mesh we'd like each of these patches to have. So what we're going to do is go mesh, edit surface parameters, and what I'm going to do here is make sure all the 3 surfaces are ticked, otherwise one of them or more won't mesh. You can put additional text in here to give specific rules for setting the min and max mesh resolution for each different patch. I'm not going to go through that now because this is just a kind of brief how-to video, but we can do another video for that later on, but that's how you would do it if you want to. So just based on the scale of the size, what I'm going to do is say I want the maximal edge length to be 0.3, so that's 3 millimeters, so I know that's kind of about that much, so I'm happy with that. And the minimal I want to be 10 times less than that, so that's 0.3 millimeters, and basically I'm just going to say OK now. And so all we've basically done there is to set up the conditions for the first mesh. So ENGRID doesn't really have a very good undo stack, so what I would religiously do is to save your complete case at predefined sensible intervals. So at this point I would save this grid, and I would save that as whatever you want, but I'm going to call it step 0. So this is just me. I've set up what the surface resolution is going to be. I'm not going to overwrite that, but that's all step 0 is. So basically now what we're going to do is to create the surface mesh. So all we're going to do is mesh, create, improve, surface mesh, and that's just going to start the meshing process off, and I would just leave all that by default, the default options, and click OK. I'm not going to click OK because it's going to take about 15 minutes, so I'm going to skip forward to the next loaded model stage, but the only difference between them is I haven't pressed this OK button. So if we just go to the next step, step 1, So here we are, virtually skipped forward in time 15 minutes, and you can see that because we've put min-max edge length, ENGRID has basically refined the mesh around the small radius areas. So you can play around with it to your own model to get it to look how you like, but for me that's not a bad first go. So I'm pretty happy with that. So I would then save this now, and I would save that as step 1, the surface mesh only. So we're going to pretend I've done that now. So the next thing we need to do is basically set up the boundary conditions. So I'm going to go simulation, edit boundary conditions, and so it's worth making a note of which number you applied to the patches earlier on when we did the P and the S keyboard letters, so you remember which is which. If you can't remember, you can just go to V and hide 1, 2 or 3 and see, you know, which ones they are. So I'm going to change the names, BC name, so just double click in the box and name them. These can be anything you want, but bear in mind these are going to be what you need to put into OpenFOAM, the case setup. So if you're doing this yourself to use in my tutorial case files, if you use different names here, it won't work because the OpenFOAM case structure's got these names plugged into it. So make sure you've got continuity there. Patch is fine for inlet and outlet, but for the main, this needs to be, in this particular case, type wall, and this information will be exported. So if you get this wrong, it won't work. So it's quite important to make sure you do that. And we also want these to define an internal volume, because these are just 2D. No, they're not three-dimensional, are they, in terms of thickness? So we're going to add a new volume. So just type volume add, and I'm going to delete that one. So this basically just means these 3 patches are going to define the internal volume, and each of them, A in, is just defining which face direction is closing off that volume. So normally that sort of works out to be okay. So that should be absolutely fine. So I would just click OK now, and I would then save that as step 2. I would save that as step 2, the volume defined. So I'm now going to go on to load step 3, which would just be exactly what I've just done, but with that volume defined. So step 3. So basically, I'll just do a section through here, because the next thing we've done is we've extruded the external surface to be a single very thick viscous layer. So basically how we did that is we went mesh, create prismatic boundary layer, and I've then clicked on main, because we don't want a viscous layer over the face of the inlet and outlet, we only want it over the main, and it's going to be working with the volume that we've defined, so you need to click that as well. You need to do both of those things. And I'm going to use an absolute height, and what I'm going to do is set the first cell height to the complete thickness of all the viscous layers we want to be 2 millimeters. Sorry, that's the wrong box, that's the relative, but it doesn't matter because we've selected absolute. It's already got the right value in it. Absolute height of the first cell So that's actually the total height, so we're going to subdivide all of that later. So basically, if I click OK now, that'll take another few minutes and we'd end up with what you've got on the screen. So if I just do a clipping through here, so we define which face you want the clipping on by typing a 1 into these boxes. So I'm going to click enable, and to make sure it sections the volume elements, I'm going to click that and turn the surface off. So I'm going to click redraw. So that's basically what we've done. Okay, obviously sectioned. So we've made one very thick viscous layer, we've defined what the volume inside will be, but we haven't meshed it. So that's why it makes a nice viscous mesh, this program, because the first thing we do is to salt out the boundary layers. So we're going to subdivide it later. So this I would save as step 3, which is the viscous layer created. So I would save that as step 3, and basically then we're going to create the volume mesh to fill this in. So how we would do that is that we go mesh, create improved volume mesh, netgen, click the volume which we named earlier and just press OK, and that will then take another few minutes and you'll get on to the next step, which I've saved as volume 4, volume mesh created. So that's what we would end up with if I'd clicked OK. So you can see we're getting towards a finished mesh, but we need to subdivide this green single viscous layer into however many layers we want, and to decide how thick the first layer would be, which, if we know what we're doing, we've already decided because we've worked out our Y plus and what we need to have for our turbulence scheme. So that's some physics that you need to sort out for your own model. I've just picked something a bit arbitrary here that happens to work. So what we're going to do now is go mesh, divide prismatic boundary layer. I think that's fairly obvious in terms of what it's going to do. So we then click volume. The most important one's obviously the number of layers, so I'm going to click 5, and I'm going to leave this absolute, and I'm going to do absolute height of the first cell. I'm going to select to be probably 0.2 millimeters. So that would be the absolute height, and that should all work okay. So I'm actually just gonna run one of the commands live, as it were, because this dividing the single boundary layer into the various layers doesn't actually take all that long, so it's not particularly arduous to sit and wait. And you can see that was pretty quick, so you can see what it's done. So we've got 1, 2, 3, 4, 5 layers, 1, 2, 3, 4, 5, and that one there will be 0.2 millimeters. So obviously it's pretty clear now how you can set this up to suit your own physics. And I would now save this as the next step, which would be step 5, layers divided. So I'm just going to load that. So this is just loading up exactly what we just had on the screen. So obviously the reason this is cut is just because I've got this section view enabled. So if you don't want that, you just untick that, and be careful to note that if you've got the surface elements enabled, they don't really section, so the section view won't show up properly. So just pay attention to which of these you've got ticked. So you see, it can be really annoying doing sections if you forget to untick that, because you can see it's sectioned but you can't actually see inside, so make sure you pay attention to that. So the only thing we've really got to do now is actually just export this mesh for OpenFOAM purposes. So all we're going to do is go export OpenFOAM, and there's some options. We're just going to do grid only, and this is just going to ask you for a folder, and all it's going to do is create basically a polymesh folder, which you're going to put in the constant directory of the OpenFOAM tutorial upon which you want to build your simulation. So in the next video we're going to show that happening, and what we're going to do is we're going to use OpenFOAM version 7, which is the latest official branch, and we're going to use the SimpleFoam Pit Daily tutorial case. We're going to put this mesh in there and modify it to run that, and that's how we're just going to demonstrate the full workflow. So I think you should probably now be pretty clear about how we do things. It's just a different workflow to Snappy Hex Mesh, so you've just really got to remember the various steps. So I've got an Excel sheet which just has the steps I ran through in the video there. I've put that on my website as well, the download link. So if you get muddled, just please download that Excel sheet and you can work through it yourself. Obviously there'll be an infinite variety of different ways of doing this depending on which geometry you're wanting to make, but my point was just to show the general workflow, because what a big problem with ENGRID unfortunately is that the tutorials it came with were not terribly easy to follow, and most of them were with geometries which are not, to be honest, that immediately applicable to many sort of industrial cases. So that was a bit of a problem. So if you like ENGRID, please get in touch or connect with me on LinkedIn, and as I'm recording this video at the end of March 2020, industrial civilization has been temporarily paused because of the coronavirus, so I think one thing's get back on track. I'll be again attempting to get some funding for ENGRID to update it to work with the latest Linux, and if we get a bit of funding together we can also get some unknown features like parallel processing and a couple of other tweaks which could really be a good contribution to open source meshing. So please go on to the next video now to see how to put this mesh into the Pitch Daily case and how to run it. So I hope you found that useful, and speak to you soon. Bye bye.